So we're here today with a new guest. Would you introduce yourself?
Certainly. My name is Pam Wells, and I'm a professor in the math department, but a colleague of John's for a whole bunch of years.
20 years.
20 years. I'm in my 23rd year at Grand Valley. And we're going to talk about a skateboard selling problem today.
And we've had a Professor Wells before?
Yes.
You
That's
ever-
my husband.
All right. So, anyhow, so thank you so much for coming. And I like that you kind of found a problem that you thought was a little bit interesting in kind of units and rate of change.
Yeah, and I've used this with my calculus students in the past, and there are pieces of it that they always find really interesting because it's not, how things end up is not necessarily how they think things are going to end up. It's not as intuitive as they think it is.
Nice.
Yeah.
Okay. All right.
Okay, so what we have is we have a function q, and q is a function of p. So q equals f of p. Q is the quantity of skateboards sold, and p is the price that they're sold at. So the function f maps the price of the skateboard to the quantity that then you would predict would be sold at that price.
Okay. So I imagine they're saying if the price is higher, they sell fewer, and if the price is lower, they sell more.
Yeah, although we don't really know that for a fact
Mm-hmm.
at the beginning, because this function f is not written out in any sort of algebraic way.
Ah, nice.
Okay, so basically all we know is this. Okay, but we don't know what that function f is, whether we're squaring things, or if it's quadratic, or if it's sinusoidal, or if it's logarithmic, or whatever. We don't know.
Okay.
All we know is that q and p are related by this function f. And we know a couple of other pieces of information. We know that when the price is $140, so f of 140,
Okay.
then we sell 15,000 skateboards. Okay, so when I look at that, I look at it and I think, okay, my input in my f function is price, so $140 per skateboard, and the output is quantity sold, so I'm selling 15,000 skateboards.
Okay.
Okay, and we also know a derivative at that same price point. So f prime of 140 is negative 100.
Okay. So it's kind of interesting to have information about the value and the rate of change, but no other information about the function.
Exactly. So it's kind of a mystery function,
Yeah.
but we do know what's happening at least a little bit right at 140 or right around $140 per skateboard.
Okay. So now you've read this problem before. Is there anything you do to like kind of make sense as you're going through?
Yeah,
Or-
when I look at problems like this, I think units to start with. So when I looked at the first equation, I was thinking 140 was dollars per skateboard,
Okay.
and 15,000 was a quantity, so 15,000 skateboards.
Okay.
But now when I go to this one, I have to pause, and I always have to pause and think, okay, what are my units now, right? This is still f prime of p, so 140 is still $140 per skateboard,
Mhm.
but that negative 100 has new units, right?
Yeah. So rate of change of what with respect to what?
Exactly.
Yeah.
And so that's, at least for me, I always have to stop and say, what's changing with respect to what, and how does that tell me what that negative 100 even represents, right?
Nice.
Yeah.
Okay. So how do you figure this one out?
Well, for this one, I'm thinking, okay, so we're looking at the change in quantity of skateboards, so the change in Q compared to the change in price, the change in P. Okay? So this negative 100 would say it's negative 100 skateboards for every dollar increase in price. And that sounds a little weird to say it,
It does. Yeah.
because it doesn't, so I would rather think about it as saying when my price is $140 per skateboard, if I increase my price by $1, I would expect that my quantity sold would decrease by about 100 skateboards.
Okay. So it is. I mean, it is as the price is increasing. At least at this point,
Mhm.
as the price is increasing, the number of skateboards is dropping.
Exactly. So we know what's happening right around $140 per skateboard. We really don't know anything about any other price points.
Right.
Yeah.
Oh, interesting. So you're right. It sounds like crazy extreme, doesn't
Mhm.
it? Like for $1. Really, there's 100 people out there who would say, no,
Right,
140, that's my limit.
Right.
Right. So, and I liked when you were thinking about it, you were thinking about that kind of another way we could write this derivative, right? Be this, you were saying the change in the quantity of skateboards per price.
Yes, per
Yeah.
unit change in price.
Okay.
Yeah. Yeah, so this is really in skateboards per dollar increase in price, which is a strange unit.
Yeah.
And so I find it easier to think about it as a ratio or a rate.
Yeah.
Okay.
Okay.
So we got that. But really, when people are manufacturing and selling skateboards, they care about the selling price and they care about how many they're going to sell. But they really also care about the revenue that they're going to bring in.
Right.
And revenue is related to the quantity sold and it's related to the selling price. And so you've got this next revenue function, and R is going to be, let's see, so if you have, to figure out revenue, you need to know how many you sold, and you need to know the price per unit, and you multiply them together to get how much money you brought in, right? And so in this case, the number we sold, that's that Q, right?
Mm-hmm.
And the price per unit is P.
Okay.
So now we've got a product. Okay, so our revenue is a product of Q and P, or I suppose we could write Q is F of P, right, times P. And now we've got R as a function of P.
Okay.
But it's a product.
Right.
Okay. And so, but then, I mean, when I look at this, the question that I want to know is, okay, we know what's happening to the quantity sold when we have a price point of 140. We know what's happening to the rate of change at that same price point.
Mm-hmm.
I wonder what's happening to the revenue at that same price point.
Because really, that's the bottom line question.
It is.
Yeah.
It's like, so here we know if we raise our skateboard price by $1, we sell fewer skateboards, about 100 fewer. So the question is, what does that do to our revenue? Is it better for us to increase the price of the skateboard, even though we're selling fewer? Or would it be better for us to keep the skateboard price lower so we sell more?
Right. So, I mean, it might tell you to stay the same. It might
Mhm.
tell you to lower the price.
Yeah, or increase the price.
Yeah.
And we need to figure out which of those this information says we should do.
Like, this feels more realistic, because a lot of times these problems in books are, here's the function for how many. So if they know that already, then they kind of know everything about it.
Right.
But in business, it would make more sense that, well, when it was priced this, we knew we sold this many. When it was priced that, we know we sold that many.
Right, you don't always have an actual function. What you have is data.
Right.
Yeah.
Yeah. Okay,
That's
nice.
good. Okay. So I guess what we really want to find is we want to find the derivative of R with respect to P when P is 140, right?
Mhm.
Because that's really the only place we can do it, given the information we have.
Okay. So this question came up once. Do you know the origin of this notation?
Not a clue.
With the bar? Okay.
No, I
Yeah,
wish I did.
I didn't either. All right. If I find out, I'll let you know.
Yeah, I mean, because when you use the prime notation, it's easier to show the point you care about.
Mhm.
But when you use this notation, it's not nearly as easy to show the point you care about.
Yeah.
But I don't know where that came from.
Okay. I was just asking, just in case.
Yeah, no, sorry. So this is actually the point where my students generally find it challenging.
Because how do we take the derivative if we don't have a function?
Exactly,
Yeah.
yeah. Yeah, and so you've got to think about, well, what do I know, right?
Mhm.
And I know some information about when P is 140. I've got these two pieces up here. And I've got this revenue function. And then I want to take the derivative of this revenue function with respect to P. And so then you've got to look at this and go, okay, when I look at that, I see two pieces joined by a multiplication symbol. So in my mind, I think that's a great application for the product rule.
Okay.
Because I have a product of two quantities that together give me revenue.
So it's really, I mean, you're looking at the kind of the structure of the function.
I am, yeah. Because otherwise, because I don't have a specific algebraic formula, I can look at this and it looks a little overwhelming
Mhm.
because I can't just start using a derivative rule. I've got to figure out what's the underlying structure of the function so I know what rule would be appropriate.
So what does the product rule tell you about this one where we don't have a function?
Well, you know, for this one, I guess my rule of thumb on these is I know what the product rule says. And so I'm going to write down the product rule, and I'm going to input my P equals 140 in all the appropriate spots. And then I'm going to cross my fingers that this information up here is going to be helpful along the way, right?
That's where kind of we trust the book a little bit, right?
Yes, yeah. Because otherwise, if this were a real life scenario and I didn't have all of the information I needed, I would have to go back out and try to find that information, right? Collect that data somehow. But given that this comes from somewhere, I think it's pretty likely I'm going to use this somewhere along the line.
Okay.
Okay.
Okay, so let's see what happens.
All right, so I'm going to do the product rule. So I know in the product rule, I'm going to take the derivative of my first factor. So I'm just going to write f prime of, and I'm going to leave it as p, and I'll plug in or substitute in the 140 later.
Okay.
And then I'm going to...
Because why?
Because I think sometimes if I do it right at the same time, I mean, you could, it's just a matter of steps. But for me, I like to see the whole product rule written out, and then I start to plug in. Because I think if I plug in my 140 for p, I lose that's my second factor, and it just looks like a constant.
Okay.
And it's not, and I have to remember that for my second part of the product rule, right?
It's literally the variable for...
Exactly.
Yeah.
But if I plug the 140 in, it may not look like that anymore.
Okay.
So I know I take the derivative of my first factor, and I multiply it by my second factor that's unchanged.
Okay.
And then I take this, I add to that my first factor left alone times my second factor, the derivative of that. And now here, the derivative of p with respect to p, that's a place where I always have to stop and be just a little bit careful.
dp.
dp. I could write that. I'm comfortable saying that's 1, right?
Okay.
The derivative of p with respect to itself is 1.
Okay.
Okay.
Just like we'd say usually the derivative of x is 1.
Right.
P is the variable.
Exactly.
Okay.
It's the independent variable. Okay, so now I'm going to go ahead and I'm going to substitute in p equals 140 everywhere I see a p.
Okay.
So let's just do that. So then I'm going to have f prime of 140. It's actually really challenging sitting down and writing like this. Times p, which is 140, plus f of 140 times 1, which I'm not going to bother to write.
Okay.
Now, f prime of 140, luckily I know is negative 100, because that's my rate of change of the quantity sold with respect to price.
Right.
And I'm going to multiply that by 140. And then f of 140 is just the number of skateboards sold when the price is under $40. So that's 15,000. And this, luckily, that's a pretty easy mental math problem. That's going to be negative 14,000 plus 15,000, and that gives me 1,000 positive. So I have a number, and then I got to stop and figure out what that number means.
Right.
Yeah. So my number is 1,000, and it's positive. So the rate of change of revenue with respect to price is positive, which tells me that my revenue function right around p equals 140 is actually increasing, which is a little interesting.
Yeah.
Because that means if I increase my price, my revenue is going to go up. Which is, if you think about it up here, you might think, well, but the rate of change of my quantity function was negative.
So you're selling fewer skateboards.
Yeah.
But you're still making more money.
Because I'm selling fewer skateboards at a higher price. And so that still allows me to make more money, which is interesting. Yeah.
Oh, okay.
Yeah.
I was thinking about the units, because you were thinking about the units before.
Yeah.
So this is kind of dollars per dollar?
It is, because revenue is in dollars and price is in dollars. So it's like my revenue changes by $1,000 for every dollar increase in price around when the price is under 40.
So that's where the dollars would come back, right? Like if we multiplied this times $1 increase in price,
Yeah.
we'd get $1,000 profit.
Yes.
More profit.
More profit.
Right.
Yeah. Or more revenue at least.
More revenue.
Profit's something a little different.
Oh, profit is different. Oh, but I bet you, because you're producing fewer skateboards, I bet you your costs are going down as well.
Yeah, unless you're producing enough fewer that like you've lost your
Efficiency.
or something. Yeah.
Yeah.
Yeah. And it's actually interesting because, you know, this is saying, we only know what's happening right at this point. So we know we're gonna make about $1,000 more for every dollar increase in price around P equals 140. But we could also come back up here and actually use this information to predict how many skateboards we would sell and then find the revenue and see how it compares.
Oh, like just
to see kind of how this quantity compares to what we get when we look up here.
and it'd be an approximation.
It would be an approximation. Yeah, it would be like a linear approximation like you do with tangent lines, right?
Yeah.
Yeah. So I mean, we could try that and see what happens.
Yeah, let's.
I'm gonna kind of put a little
We
space
need
over here.
New space, more space. We could turn the board around.
I think we can do it here
Okay.
because we know that we sell 15,000 skateboards at 140 bucks. But if we go up to 141, using our tangent line approximation, our linear approximation, we're gonna sell 100 fewer skateboards.
Mhm.
So so our Q is gonna be 14,900, right? Skateboards,
Right.
100 fewer. And then our revenue at $141 per skateboard is just gonna be the product. If I sell this many at this price each,
Mm.
and then our revenue at 140 would be 15,000 at 140 each, right?
Mm-hmm.
And we can compare those two, and they should be somewhere close to that in terms of their difference, right?
So we would compute and we'd expect revenue at 141 to be around $1,000 more.
Yeah, it should be.
So this should be $1,000 more than that.
Yep. And this one would be harder for me to do mentally.
Yeah.
So I would want to choose an appropriate tool to figure that one out. But I would expect this to be about $1,000 more than that.
I tend to Google these amounts if I'm working at my computer.
Sure. 2,100,900.
Yeah.
So they're actually $900 apart.
So why wouldn't it be this full $1,000 apart?
That is a great question, isn't it? Boy, that's really messy.
Not by my standards.
I mean, because you think about it, this is a linear approximation, right? I mean, no matter what our function looks like, if this is our revenue function up here, I don't know exactly what it looks like. And here's 140 maybe.
Mm-hmm.
Maybe our revenue function's looking like that. We don't know. And then this is our linear approximation.
Mm-hmm.
And so actually, let's see if that even makes sense, the picture I drew. Because I just drew something kind of randomly.
Yeah.
So using the linear approximation, which is the tangent line, we predict $900 difference, which is an underestimation to what our actual product rule gave us.
Mm-hmm.
Okay, which was $1,000 difference. So that makes sense that the tangent line, the way I drew it, is underestimating the actual function. So that tells me something about the function, right?
Does it? I mean, I genuinely don't know here, right?
Okay.
Because I mean, we only have the information at that point, 140.
Right.
I mean, it's interesting to me if that does tell us something about the concavity or something.
Yeah, see, I'm thinking, I mean, it would make sense typically when a tangent line underestimates a curve, it's because the curve is concave up,
Mm-hmm.
right? So it's increasing faster than a linear function would. And since this is under this, that leads me to suspect that the function is concave up right around that point.
Oh, that's just fascinating because we don't have any information about that.
Yeah.
So if we could tell that just from this kind of the original point and then the rate of change at that point.
Yeah. And I guess I can't say 100% that I know that,
Mm-hmm.
but that's certainly what I suspect given the information I have.
So did the problem go here or is this just
No,
kind
that
of
was just me
you
thinking.
Yeah.
The problem, as it was written in the book, just asked, should the company raise or lower the price of its skateboards to increase revenue?
Okay,
So it would have stopped right here.
Yeah.
This was more me going, well, wait a sec, let's see if I can verify that 1,000 some way.
Yeah.
And getting this and then thinking about, oh, well, that's close to 1,000. It's not exactly 1,000. And kind of the same process you and I just went through is, why isn't that exactly 1,000?
Yeah. Very nice. All right. Anything else? You said you've used this with your students?
I have.
Anything that your students noticed about this?
The one thing that probably prompted the most discussion is the fact that the derivative of f at 140 is negative. And it really bothered them that we should increase the price anyway.
Yeah.
Some of them didn't want to do any of this work. They wanted to say, well, look, right there, it tells you the derivative is negative. We're going to sell fewer, so we're going to make less money. The revenue will be less. But so this interplay between price and quantity, just because the quantity goes down doesn't mean the revenue goes down.
Yeah, so I'm very visual,
Mhm.
right? So when we introduced the product rule, we did it with kind of area,
Sure.
right, to look at that. And then it turns out you can ignore that kind of second order
Mhm.
effect using Newton's magic hand waving.
Yes.
Right? So, but I was thinking about this as a rectangle, right? So it's like at 140, we've got this rectangle that's sort of tall, but then really long compared to
Yes.
how it is.
This is
So
the 15,000.
so this is the 15,000.
You want another color?
So, oh, great idea. So we're comparing kind of the area, if we make it just a little bit taller
And a little bit shorter.
and a little bit shorter.
Yeah, that's a great visual. And so you can kind of see like we're cutting off this part, but we're adding on all of that.
Because that was the longest side to start.
Yeah.
Yeah.
Yeah, so that's a great visual to kind of make sense of why the revenue actually went up.
I wonder if this square is the difference.
You know, it could be. Let's think about that for a second. So this is
So this is 1.
100 right here.
Yeah.
Oh yeah, that's the 100 right there.
Aha. All right.
All right, so you know, it's interesting how a different model can all of a sudden shed light on something that wasn't clear before.
Yeah. All right. Anything else you'd want to share about this one?
I don't think so.
Okay. Thanks so much for talking to us.
Oh, my pleasure.
All right. This was fun.
Yeah.